Right.
Okay.
Cool. Yeah, so I am happy to introduce Dr. Brian Kwan. He is an assistant professor in the Department of Health Science at Cal State Long Beach. I actually met Brian at JSM in 2019 when we were both graduate students, and he was you were part of, I believe, UCSD's inaugural PhD biostatistics.
Yeah.
Like
We're
cohort, correct?
we're guinea pigs pretty much.
Yeah,
Guinea
that's what I
pigs.
remember hearing when
Yeah.
we were at JSM at the Mixer. And then he went down to 5/405, graduated in 2021. Then did his postdoc at UCLA under professors Dom Lecenterk and Catherine Trigger, who do a lot of work in functional data, which is what he's going to be talking about today. And then went back south off the 405 to Long Beach. And yeah, I'm just excited to, he's going to be talking about multivariate FPCA for novel outcomes and eye tracking experiments. And so I'll leave the floor to Brian.
Thank you, Eric. It's a pleasure to be here, actually. So, I got a chance to be in a research team meeting, some of the faculty, and see some of the student work, and it's been a blast. I couldn't help but take a picture of some of the data visualization you did with it's really wonderful to see. And the curriculum is so unique that I was glad that Eric, basically you get a chance to have me give a talk here, even if it's a talk based on some of the work that was done at UCLA too, but finished in Long Beach. So I affiliate with a new institution here, but not far from now. So for today, I'm presenting my talk on constrained multivariate functional principal component analysis for novel outcomes and eye tracking experiments. As you can see, there's a couple of domains comprised of the title, but this is the methodological work, my most recent methodological work that I'm showcasing. So, okay, so background here, the domain working unit that motivated the methods work that I've done is in the area of ASD, or autism spectrum disorder. So when you think about it, compared to typically developing peers like PD, usually individuals that are diagnosed with autism spectrum disorder tend to experience three key things. Usually they have more challenges with social communication, difficulties in processing sensory information, and typically exhibit more restrictive repetitive behaviors than their typically developing peers. Now, as you can imagine with ASD, it is a very highly heterogeneous concept study. Particularly, the heterogeneous part is more about the extensive variation with many different phenotypic characteristics exhibit, such as attentional, social, cognitive among individuals with ASD. But notably, social attention is a core area where ASD children exhibit defects. And as such, a necessary area that's been growing, especially in biomarker development, ASD, is to look into objective, sensitive assays for social attention. And what we've been working on here is looking into highly promising biomarkers, particularly ET or eye tracking experiments. Eye tracking experiments help to study social attention aspects. So you can imagine eye tracking experiments, you get presented with like a video or image, and then you look at it a certain duration, and it might catch you certain things on the image or video playing, and it basically keeps track granularly your attention across different regions in such an image or video. Yeah. And usually that's very powerful because it provides moment-to-moment gaze patterns. You can imagine drawing like the gaze patterns with your left and right eye across the image or pattern over time. This is very also safe and non-invasive, and this can be done with children much more feasibly. Particularly eye tracking experiments tend to be working very well from infancy to adulthood. So we want to use these eye tracking experiments to look into biomarkers so we can understand more about ASD heterogeneity and also investigate more differences between ASD and TD. Okay, so in creating better biomarkers for ASD, our work is motivated from study data based on the eye tracking battery that contains different social attention constructs in the ABCCT study, or the Autism Biomarkers Consortium for Clinical Trials. So this consortium is part of the group I started working with as a postdoc at UCLA. In this study here, there are two well-known batteries that we're investigating, the eye tracking and EEG. There. So the EEG, just to put it simply, is like looking into brain waves. So using the brain waves as like biomarkers to investigate for ASD, those two are of interest to investigate. But for today, the focus for this methodological work, we want to hone in our focus on one of the eye tracking tasks in the battery. This is the activity monitoring. In this type of experiment, individuals are presented with a series of images or videos, and each unique image or video would be considered a trial. What's common among these video images is that it involves usually two people engaged in some joint play activity, and that could vary based on, so you have several unique trials. Now, in looking at those people with joint play, there are several regions of interest we keep track of where they're paying attention. As you can imagine, when you have people, do you look at their face? Do you look at their torso? Do you look at their legs? Do you look at their arms? Especially if it's a video when they move. How does your social attention change when you're looking at different things, when you're gazing? So here's an example of a trial. This is actually part of a video, screenshot part of it. So you can sort of see there's two individuals in play. So their eyes are redacted more for privacy reasons, but in the video, the eyes are actually there. So this type of video is basically played for about like 20 seconds, where you see these two ladies. What are they doing is basically they're cleaning the toys and putting them in the box. And they do that for about like the 20 seconds. And when we have our participants, which are school-age children in the study, they will look at that and we'll track their gaze patterns, for example, based on a legend here in color. So you can imagine the faces, the two red spots represent keeping track of that region, which is their attention to the faces. The green shows more like you can see the toys and then the arms that are involved using their movement and action in the activity, which is why it's called activity monitor, let me say. And then everything else here, the blue, would be considered like a background. Here. We do collect multiple regions more than this. It's just we wanted to collapse it for now to develop simplified our development with the methodological work. What's not also here is that since there's 4 regions in those 3, is that we also have non-valid data. So sometimes kids may not be paying attention closely to the experiment. They look off screen and that is captured as part of the time in the trial. So this would be considered not looking at screen data, which is non-valid here from this case. And with each of them, you can imagine there's a certain proportion of time spent in each of them too. To put it simply, when you're doing the eyes gazing, you're like, do they look here, here, here? What does their gaze pattern look like in the span of 20 seconds here? But we can collapse that information to see how much time they spend in each one. There. Oh, yeah. So typically, conventional analysis of eye tracking data collapse information within and across trials. So again, a trial is basically one image or in a video. So the outcome would be like a gaze path, right? But that's can be seen as like a curve that goes around within a square box. And they would take that information and simplify it out to just calculating proportions, looking time, like keep track of where that gaze is being located in each region and calculate how much time is being spent within it. So the ROI is the region of interest. They also look into averaging outcome across trials. So if a person went through 16 trials, which is like 16 unique videos and images, and they spent the time looking at faces in each of them, can we average them across all 16? Sometimes they also simplify in that fashion. And typically they also tend to analyze each attention to region separately too. So you can imagine there's multiple things you could do to also provide a more holistic analysis based on that. So some examples of doing it conventionally, you missed out on content like, what's the video or image that was used? What's the activity type? Among the multiple categories, like, is there dependencies among them when you're looking from one to another, sort of like a transition between relationships in the different regions. So we want to capture some of this complex relational structures in this high dimensional looking data. So this motivates our methodological development. So the first thing we wanted to try to do here is that we wanted to create a novel, a multivariate functional outcome for this experiment here. First thing, part of this outcome here is that this will not collapse information across trials here. So with this in mind, each trial will be considered uniquely in describing this outcome. And you can think of it as sort of a trial index, you'll see, sort of like time going through time, but then instead of like going through trials here too. So using this trial index will be based on the detailed content. So we will preserve that information by considering each trial uniquely within it. And this sort of draws into the idea of the functional data methods, which is based on the theory and analysis looking into curves, objects, more general shapes. But these curves tend to also preserve the sequential information among them. And the sequential information we want to propose is the new trial index we want to say. Also with this outcome, because it's multivariate flavor, we also want to capture jointly the different proportions of looking time across different regions here. So you can imagine multiple components in a little parentheses, if you think of it in terms of a math notation here. But also understanding specific to this experiment, what are the constraints we have to impose to provide meaningful interpretations? And that means incorporating the dependencies among them. As with the unit of a proportion, it's on a scale from 0 to 1, right? So within one trial, basically have to sum to 100% of the time spent in the experiment. And each region will get its fair share chunk among that 100%. Maybe if they spend 25% of the time in the faces for a trial, it'd be like 0.25. That would be the proportion. But the restriction is, among them, they have to sum up to 1. So if you consider this multivariate outcome, each component, they must definitely have a constraint in that fashion. Now, taking this outcome into account, we want to model it. So we propose our method, which is the CS-MFPCA as an acronym. The constraint, because constraint is taking it from part 1B. That's the namesake extension for the multivariate functional principal components analysis here. So what we wanted to do, the reason why is also to use this to model the trends and patterns is to target the dominant directions of variation. See exactly the variations in ASD and TD attention. After all, ASD is heterogeneous. It's only fitting to want to investigate variation among that group and also between the groups ASD and TD. But also in basically developing these curves that also have its own flavor of understanding variation, every person can have like a predicted trajectory of attention across trials. So in a way, we'd also be modeling and predicting and developing sort of like functional biomarkers, let's say. Functional biomarkers containing information based on a whole curve to be able to study patterns in social attention, which is different than using like a scalar value or a longitudinal scale in that sense. So an overview of the data we use ABCC study to develop this methodology is that it is a multi-site naturalistic study. Our focus for the participants is based on school-age children of ASD and their TD peers. So the school-age children focus is 6 to 12 years old. That's the target range we've mainly got. Data collection was based on looking into 5 sites, Duke University, Boston Children's Hospital, UCLA, University of Washington, Seattle, and Yale University. And from this data here, we have 399 school-age children. Here you can see here on the column, 280 ASD kids, 119 TD kids, the mean age of about 8.5 years old here. One thing to note is that we did try to collect as diverse a sample as possible. But especially when you look at sex here, ASD tends to be more commonly diagnosed in boys than girls, at least indicative based on the study collection here, this data here. So among these 399 kids, the data was collected with like the different trials and eye tracking experiments and 3 different time points. Time 1, baseline, time 2, 6 weeks post baseline, and time 3, 24 weeks post baseline. And at each time point, they completed their battery of eye tracking EEG measures. The one we focus on that's collected across the time points is the activity monitoring. And more flavors on that here. So the activity monitoring task, just to give a rough idea, you saw the image, but just to put it into some context here, the participants have either a video, dynamic video, or static image of the 2 actresses, which is the 2 people engaged in joint play. We have 16 unique trials to choose from, evenly split down the middle. There's 8 videos and 8 images. An example of such an activity, you saw it was about the cleaning toys. That was the image, but another one could be like they're building a tower out of blocks. So like the opposite, they're pretty much playing Jenga, for instance. Video trials, which is the 8 of them, last 20 seconds each, and there's audio. The actresses spoke in a manner that's easily understood by children. Or again, 6 to 12 kids are watching this. In the image trials, looking at a static image 10 seconds, there's no dynamic activity related to that part, but a wordless soundtrack was played. So there was audio involved in the 10 seconds they looked into it. And at any given moment, so if you think about the 20 seconds and 10 seconds, they had to have been looking at one of the regions of interest. Of course, like the faces, for instance, there. So now you can sort of see how this plays out with this activity monitoring here. By combining the several eye tracking regions, we narrowed it down to 4. Again, we considered the 4th region here non-valid, which is not looking at the screen because kids might not be focusing on traditionally social stimuli. But again, this is just one instance of that. But because we know there's 4 regions, we can think of these as like each its own little outcome and the proportion looking time spent on them. And so thinking of the methodology, let's look at the multivariate functional data portion and how to use it. Okay, so multivariate functional data, to put it simply, in a simplified fashion, think of the outcome like this here. I mentioned in the earlier slides we're making a novel component, but let's start from the roots of that. Here, it bolded x of t to signify a vector, t being usually time in this case, made up of several outcomes here with p, length of p here. In each element here is defined as such, going from t to the set of real numbers in the L2 space of square integral functions here. As with the outcome, it also comes with a mean, expected value here, and a covariance to account for the dependencies between the several components within the outcome here. And now, as you can see, since we have maybe 4 regions, you can think of p equals 4. Each one can represent a region of interest based on the quantity of how much time they spent there. So the building blocks of how you take that into the novel outcome we have, you can start from step 1, that our units of interest is the proportion of looking time and an ROI, and each ROI represents each of these P's. So that basically means now the range has to span from 0 to 1, limited for each of them here. So that's the first building block for that. When you go to the second one, now you have to consider that because in the experiment, they had to have been looking at each of these regions of interest within the whole experiment, the proportions have to sum up to 1 at the end of the day. So that's the constraint sum to 1 for any particular trial T. So consider the T part as a trial. So there's 16 of them, could be from 1 to 16. So therefore, we have what we call a within trial. So for a value T, dependency constraint. So adding these up, it should sum up to 1. That our outcome should always adhere to that for experiment. Next is that the trial index T, which is what we're using, will be based on the trial specific contents of the eye tracking test. With time, you get a sense that, oh, T equals 1, or I mean, T equals 0 is like baseline, and you think of T equals 1 as like a couple weeks out, time equals 2, another couple weeks out. Here in the trial index, we do things a little differently. What we wanted to do is basically have this T sort of serve as a value order going from ascending order based on interest and activity region of interest. What this means is that this T value should take values from 1 to 16 based on the 8 images and 8 videos. But the way we sorted them out is based on which images on the lower value have the least amount of interest looking at the activity region part of it. Basically, the plain toys. Higher values of T basically says those videos, images, kids really like to see what those 2 actresses really did. Here. So conceptually speaking, this trial index can think of it as increasing level activity interest here, which is basically the namesake of the experiment, the activity monitoring. But it's more fun to look at it in this fashion here. So give an example of how this would work in action. So consider for a trial index T, which is a video or images and the proportion of looking time in the 4 regions of interest. That's what it would look like if you strip off the map. So face, activity, non-valid background for some value T here in red. This T can take any of these 16 values here. And this is the first 8 is the images and the last 8 is the video. So that's the 16 unique trials that can happen. And this was sorted out based on the interest in the activity for constructing this index here. So how to interpret this here is saying the most boring trial we saw was for kids to look at an image of the 2 actresses holding down a box. Not so exciting, right? So therefore, that's not much attention at that. And then maybe the most exciting thing we saw in activity was the rank 16, highest. Watching 2 actresses as a video, not an image, crush the Play-Doh for 20 seconds. More interesting than, say, taking turns chopping vegetable toys, or pretend writing and erasing, or finding the fish toy from a basket. Makes sense, right? Because your Play-Doh, when you watch someone, you're like, what are they gonna make? Like, my attention's focused on what are you trying to create out of it? So it lends well to understanding a little bit about kids' social attention there too. So think of an example, say, for trial index 10. So they were looking at cleaning toys and putting it in a box. And this person is this ASD individual. So they can have this kind of example as a value outcome. 25% of the time spent looking at the faces for trial 10, 45% looking at activity, 20% looking off screen, 10% in the background. And that essentially adheres to the constraint. This ideally is what the observed data is like. And when we model this, we also want to adhere to this constraint here. This is a necessary condition. Now, this is for a specific value T, but what does it look like if you decide to take it out functional nature here? So one of the things we want to compare is, why did I do this activity ordering? Why didn't I just do chronologically? Well, one thing to note here is that if I did it chronologically, and this is actually just the mean raw trajectories taken across 399 kids. No, it's not split by ASD and TD. This is a demonstration of what it'd be like going from 1 to 16, and each color-coded mean trajectory represents the faces, social attention. So the y-axis is scaled from 0 to 1, which makes sense here. The reason being this chronological order is not something we want to really use, is that in the experiment, a person's trial 1, when they're given first, is not the same video or image another person can get. This is by design due to counterbalancing. So, but in trying to preserve that part in the statistical interpretation, it gets lost. And so here you tend to see a lot more noise, a little bit harder to make certain of make sense of the trends and patterns. And we wanted to try constructing our own trial index, what we saw earlier, based on activity ordering, which means every person's trial 1 is that same boring image, and every person's trial 16 is that same most exciting video of playing Play-Doh. And by doing so, this is what it would look like here. And this is, again, mean trajectories across 399 kids for their proportion looking time. Here, the green here, by construction of the index, it should be increasing all the way. really, because it's sorted by activity, interest, trial index. But you see other cool things out of it, like, oh, more time spent looking at activity, less time spent in the background. So it obviously your attention can only be divided so much among that time you're to compete with. But the faces in red and the non-valid looking time is also here as well. So going forth in this analysis, we are using this trial index because it allows us to essentially, eliminate more noise, easier to see functional data, to see more clearly defined features like curvature, smoothness going forward. That's very specific to this experiment. And plus, it helps to know, since this whole index is based on activity, how do the attention span for them co-vary based on increasing activity? And we see like the background, for instance, is going the other way here. Okay. So now, so again, the index is based on activity ordering interest. This is just based on the data, no modeling just yet, but split by ASD and TD. So the TD kids, mean trajectories overall so these are calculated by with 119 TD kids, and the orange is with the 280. And you can sort of see that typically developing kids tend to be more consistently spending a bit more time looking at the faces than those in the ASD across the trial index. Activity, pretty more even in terms of closing the gap. But the time that TD spends looking at the faces more than ASD also translates to less time spent looking at off screen or in the background, a little bit here to show. But of course, this data is sort of just like looking into it descriptively more so too. And we want to sort of model this, but also get a sense of variations from it. So this is where the idea of multivariate FPCA comes into account. So the functional principal components analysis. So for the I subject, let their novel outcome we saw earlier, but then let's put a subscript I. So this I could be from 1 to 399 here. And P could be 4, because we have 4 regions for novel outcome. And multivariate FPCA can be expanded to model as such. Take this individual's trajectory for social attention in the region. And based on this, you could do a truncation that's modeled using an overall mean here in mu t. And notice that it's in bold. So the mean is also multivariate because you have to have a mean for each social attention here. And this will help capture trends in social attention. And then now you add other components that give it a unique flavor for the subject here. Here, if M is the number of principal components you can select to include in your model. Now, each of these captures dominant modes of variation, with the first one capturing the most, and each successive one capturing less here. And like the mean, these functional principal components are multivariate because they're also in bold. So the first component will have, variation curves for each of the regions. And here, rho, this is not bold because it's not a vector. This is a scalar because it also has 2 subscripts, I and M. So with each functional principal component associated comes with their individual score. And a person can get as many score values based on how many components you decide to select in your model. So while the principal component themselves capture the dominant variation, the scores provide the direction and magnitude for variation for individual subjects here. No, because looking at it, that's what gives that individual flavor, kind of like almost like a random effect, if you think of it here. And the number of principal components we decide to select is based on the scree plot, basically a certain cutoff based on the proportionate variance explained we want to do. The multivariate FPCA method we want to apply is Happen-Greben's method. So the reason why I want to use this method is that it helps estimate these trajectories multivariately by looking into the univariate expansion. So it fits functional principal components analysis separately for each of the components in the outcome, or in this case, regions. And it takes into account the covariance matrix of each of these scores from them separately, and uses that to help estimate the multivariate components there, which is the phi and phi here, shown here. So as an example here, if we apply traditionally Happen-Grevens method, like the way they do it, this is what it looked like for one subject. But in this case, it's actually from the real data, one ASD subject here. Red is the faces, green is the activity, purple is the non-valid, blue is the background here. And this is what one person's data would look like from the modeling here. But you also probably thinking, okay, this might be a little hard to see, is that I actually put in the values of what the proportion of looking time was for that region at trial 1, 6, 13, and 16. The issue with applying direct application of this already existing method is that if you look at some of the trials, like trial 1 for this person, the constraint is not adhered from the modeling. In fact, it sums up to saying this person spends 96.3% of the time in the experiment across 4 regions. But then where did the rest go? It's just sum up to 1 because the non-valid is supposed to capture off-screen data. So the model is not capturing this constraint, which could be an issue if we're trying to make use of eye tracking experiments to look into ASD biomarker research. So here, that's why we want to propose an extension that makes up for this constraint here. And our algorithm to do so is actually pretty simplified, I imagine, interpretable for collaborators, which is what we want as our strong suit. So first here, consider a transformed version of the outcome. We used X, shift over to Z. So bold Z, but the dimension is reduced for the transformed outcome. You go from P to P minus 1. And that's because we're using essentially a natural log transformation that makes take into account one of the regions to use as the reference or denominator here. So if it's 4 regions now, you have 3 components for the transform outcome here. And what we do with that then is we fit the traditional multivariate principal components analysis with this transformed outcome based on a chosen number of components. And what you find is a very similar structure as before, but now your outcome is the baseline transform, and the mean and principal components now follow the interpretation of the natural log odds here, similar to like before here. As you can imagine, the reason why we're also doing this and making sense is because it's based on, more classical regression theory, like logistic regression, generalized linear models. And we want to try it out and see how it goes. After fitting the model here, now you have to convert these log odds trajectories, each of these components back to the original scale. It only makes sense not to talk about log odds in social attention, but just traditional social attention. So the reference in each of the components will follow what you would expect to convert back, like kind of converting probabilities here. So nothing new per se here too, but notice here that the conversion is for like every trial here. So we're basically converting whole trajectories in that sense. And by doing so, this algorithm provides a statistically implementable, pretty consistent way to yield individual trajectories that adheres to our novel outcome. By doing so, we get a success story with the same person here, but this time now the prediction actually works for trial 1 and for the others. But I'm just highlighting trial 1 because now it actually sums up to 1 here. So then at least now we can say, oh, they do spend 100% of the time in each trial, which makes sense, experimentally speaking. But obviously we had to back transform after going log odds to do so here, which is here. This is for one person, but I wanted to look at, for instance, here, each of the regions for the same person and seeing how it does. So here, the solid dashed line is the observed trajectory based on the data. The dashed line is the smooth, and then the very ... is our model. If you can see that there's quite a bit of overlap, that's a good thing. In fact, if you see them very differentiate apart, that's not a good thing because then our model is not even following what it should be here. The reason why we want to compare it to the spoofness is because we wanted to target underlying trajectories not dominated by the noise in doing so. So in essence, our model is capturing core patterns in the data. Some interpretations here. As we move into the variations, you're going to see much more like log odd stuff, but just to put it into account, like this is what the transform outcome looked like before transform. But the multivariate components are gonna follow this scale. And so when you think about this here, the background is serving as the reference because usually that's the part that's non-social, and it's usually the part where it's almost all the kids have like non-zero time spent, at least compared to the other regions. And if you think about it here, so the first component of this transform outcome, faces versus background. If it's greater than 0 log, then you say greater relative time spent looking at faces versus background here. And if it's equal to 0, then you basically spend same amount of time faces and background. And if it's less than 0, well, that's basically saying the value indicates the person spent less time looking at the faces than the background. So keeping this in mind for the variations. So moving forward, I decided to fit each of the constrained multivariate functional principal components analysis models separately by group so that I can allow their core functional components to differ by diagnostic status. So they're separate models here, 2 models rather. So here is an example of the mean function from the MFPCA. So of course, now your attention can be zoned in on 3 components because the background is the reference to all of them here. For the sake of interpretation, we'll go through a simple example with this. So this is the AST model. We're looking at their mean functions for the transform log odds of mean time. If the green log passes through 0, then that means they spend more time looking at activity than the background. If it's less than 0, then they spend less time looking at that particular colored region versus the background. Take for instance here for the AST group. The green line is showing that they are spending more and more time based on increasing the interesting trials on the activity than the background, which makes sense because then the videos are showcasing that they spend more time on that activity than it is in the background. But then you get things like these, like the mean curves for faces and on-out, which are consistently negative than log odds value. So it's almost like saying here, ASD, they spend more time in the background than the faces forward-looking odds. Yes. Yes.
I was really struck with looking at the data you've been sharing, that it seemed like the ASD and the TD had similar patterns of looking at the activity. I was wondering, did you think about maybe having the activity as the reference rather than the background? It's kind of like a zero sum, like it seemed like both groups had very similar activity looking patterns, but the sort of a zero sum game with the other other activities, other components.
Yeah, I think that we were thinking about that initially, but the thing is, we also had some interest in the face, and it didn't fall too much behind. So it was like, well, if the activity is going under, you might as well look at face. But the thing is also in terms of like mathematical properties, among the regions, the ones that has non-zero data so it's good for the denominator would be the background. So kids at least spend at least a little time in the background. We've observed many cases where sometimes kids would spend 0 time like in the faces. So they would be knocked out for the sake of simplicity what we're trying to develop here. But that's a good point. That would change the interpretation. The units get flipped. Yeah. I think the red curve here is interesting, like the TD group actually gets very close to 0 for trials greater than 8, which is saying that, okay, for typically developing individuals, for the first 8, which are all images, they spend more time looking at the background than the faces. But then once they get to the videos here, they spend almost close to equal amount of time looking at the faces and the background. So not only are we looking at it, I mean, I can't say we're doing direct inference, there's no p-value, I'm not doing bootstrap or any of that, but when you look at that way, it's sort of like, you can sort of see these differences, not only within group, but between them.
Well, you were saying the videos, the people are talking.
Yes.
Well, wouldn't that draw, consider the TD to look at the face? But apparently the ASD don't look at the talking lips. That's what it seems to say.
The sound could play a role, yes.
Okay.
Yeah, as we mentioned, yeah, because they would hear the activity going on. So sometimes they would communicate the 2 actresses a little bit, but using very clear language the kids will understand.
Okay,
So,
but still,
yeah,
somebody talking, you tend to look at them.
yeah.
Okay.
Although the time spent looking at them is, yeah,
Yeah.
a little bit different. Yes, yeah. Now, I wanted to look in the dominant multivariation. So this is the first principal component, which accounts for 59 point, about 60% both, and separate models, of course. So each of their components actually account similarly. And the way to interpret this, saying simply, is that if you look at the values in the component, if they're more differentiated from the center, which is 0, they're contributing more to the most dominant component. So what explains the most variation, the most dominant modal component here for the ASD is actually in the faces. So among ASD kids, what really separates them among social attention is how they spend looking at the faces, more so than the others. I mean, yes, so you have off-screen looking time, but the faces slightly more so. And for typically developing kids, what really differentiates their social attention is how much they do spend looking off-screen. Not so much with the faces here. So we're seeing in the most dominant mode that there are some observable differences in the variation going forward here. Now, if you look at the second component here, the story kind of gets flipped a little, although it's not as much in your face with this one. So the second component accounts for a little over 30% for each of these two separate models. And now the script gets flipped with the ASD saying, oh, in the second dominant mode component, it's how they look at off-screen as contributes the most to this one, and the faces for the TD. So the main story with the two components explain about 90%. What really differentiates them amongst within each group and between them is how they spend looking off screen and looking at faces within these trials here. But ASD more so faces, TD more so off screen because of the first component here. The third component, which contributes a lot less, is actually very interesting. They're both based on the activity. So the activity is contributing to the third component, which explains like 10% or less for both models. But you can sort of see with the TD that variation could be also very trial specific among them. So the trial contents may be carrying some of the leftover variation from that pattern here. Yeah. The last thing we try to do is we want to see how well our model dispredict the trajectories for people. So we wanted to compare subject-specific trajectories using the traditional method, MFPCA, with our method, constrained multivariate principal components. Based on not just the observed data, but we want to look at predicting their underlying smooth versions that respects the dependency constraint. So taking their observed data, we smooth it after doing a log-odd scale so that we can obtain prediction errors that are not so dominated by the noise if we did use observed data. And the smooth versions of the raw data would also respect the dependency constraint of summing to 1. So the algorithm we went to evaluating prediction performance is take this log transform outcome Z again. So again, that's 3 components for our example. Smoothen each of these out using like low S. Convert the smooth transform data into the original scale. So back transform them to X, but then we call this X tilde here. And now we obtain X hat, which are the model predictions from both methods, and evaluate the prediction error metric using relative squared error defined in this fashion here. So looking into relative square error, this is a metric that's calculated for each person at each region separately. So a person should have 4 values like this to contribute. 1 for the faces, background, activity, and non-valid here. So putting this here into a box plot. So this is for the ASD group. So this is using the ASD model, predicting within ASD here. So here, the 4 regions are shown on the x-axis and the relative square error values are shown here. And you can sort of see higher values is supposed to be not good. The red represents the traditional multivariate method, and our blue is the constrained version here. For the ASD group here, there's lower error for the activity and background, so it's not doing too bad. But in comparison, the faces of the non-valid regions tend to display higher values. With at least our method doing notably better for most of the distribution than what was traditionally, the traditional method would do so. And what's interesting is that the two regions that have the most error are technically also the ones that have the most variability. From the components, these are also the two with the main story. Looking at it from the TD side, it's more so with the non-valid region here. So the non-valid data also was identified as a leading variation, especially in the TD group. But notably here that the gains from our model, from respecting the dependency constraint, that's the main difference, is probably pulling a lot of weight to be able to justify the lower prediction errors for most of the time for the subjects here. So again, for these box plots, it's based on 119 people for TD and 280 for the other. So overall contributions, our methodological strengths look into the intersection of functional data analysis and eye tracking experiments to provide a practical model development and give strategies that will help understand our ASD and further eye tracking based biomarker research. Our work was look into developing a novel outcome that uses a unique trial index that preserves information about what each trial really means there. By doing so, we're able to model trajectories that of looking times jointly across multiple regions, so co-varying, and in essence, basically develop this new estimation algorithm, CMF-PCA, that accounts for these eye tracking constraints and features we have there. So this work also extensions for the future that includes, for instance, my research is looking into novel methods for hierarchical, longitudinal, multimodal, and multivariate functional data with practical applications. So I'm also very on the applied side, if you're wondering. Some of the extension of this work using that is looking into multiple functional layers. I didn't look at the gaze path. I was collapsing that information at proportion time, but then there's a functional nature attached to understanding granularly what would it be like if I took the whole gaze path, yielding much more information than what we have. But this is a good start here. And by doing so, these gaze paths also unlock to understanding how the transition patterns work across time within a trial. Other things include building grouping variables and covariates into a model to allow more direct inference. So it can provide more like concrete statistical conclusions and effects. And also the data has EEG measures too. Eye tracking is more of a behavioral biomarker. EEG is more like a brain wave, which is its essence is pretty much saying the function. What would it be like to combine both modalities into a model and harness that information doing so? And this is actually of interest to the National Institute of Mental Health when I gave this presentation. We have it once a year, this ABCCT group that usually have people like FDA who are looking into this biomarker research, and they want to kind of see this kind of work come to fruition here. So key references, this work is actually published in Statistics and Biosciences here. Some other references drawing from the previous multivariate principal components analysis method and our paper that looks into our ABCCT study and the eye tracking battery that comes with it. Great recent paper, 2022 comes with it here. So it'd be great to talk more about this. So I want to acknowledge my postdoc mentors that helped kickstart that project and then finished it up when I was a faculty member, Catherine Sugar and Damla Center. So they're biostat faculty, wonderful mentors, facilitate my development towards staying in academia. And the ABCC study, which consists of many wonderful people that have this rich data, providing me this opportunity to learn more and gain statistical methodology, expertise, and functional data. This work was supported by the R01 and the U19 grant. So this U19 grant was initially funded also to help pay for my postdoc training too. And so thank you very much. This is my Long Beach email for your questions.
Any questions? Ryan does have a short thing he wants to add sort of at the end here about a program of interest to everybody here, but give a chance for everybody with questions.
Happy to take questions after too. It's okay too. If pizza is still on the table, so don't disturb your meal.